So next up is Connor Hart, who is the CTO at startup Quantum Catalyzer.
I'm going to switch sides with you. Thank you. We'll see. I'll try to talk fast before the sun gets us. Anyway, so you already can't see it. Thank you, though, for the introduction, Will. My name is Connor Hart. I'm a physicist by training. I'm currently CTO at this startup that maybe if I go forward in a second, we'll be able to see it. But when we talk to you about quantum sensing, there's a lot of the same systems that folks are using for computing and networking are equally useful and valid for making sensors out of them. This fragility of quantum systems, you can kind of turn it around and make it an advantage of your system. So our mission at Quantum Catalyzer is very much to solve this kind of potential barrier that Will was describing, taking things from physics labs into actual successful products. And so this is where this catalyze, you're catalyzing a chemical reaction, that's where the name comes from. So in particular, we are sensing focused, and we're doing a number of things, IP development, maturing different technical platforms, different quantum systems. But really the big goal is to, found and create portfolio companies, which I guess you can't see it at all, but that are market specific and market focused. The team is familiar and experts in these areas, and that the solutions are tailored to that. And that ultimately we have this structure because we have, as much as they are very specific to applications, there's a lot of commonality, and we don't want to reinvent the wheel when you have the same platform technology applied to different applications. So I'll kind of today highlight one of these platform technologies, solid-state defects in Diamond, and then our kind of furthest along portfolio company in this area using this technology. The sun is terrible. So platform technology, quantum defects in Diamond. You basically imagine kind of an atom or an atom-like thing that's trapped and frozen in the crystal lattice, but it has a lot of the same properties, discrete energy levels, coherence times that because it's well protected in the lattice, it's kind of like its built-in vacuum chamber and cryogenics. And so you have coherence times that are millisecond scale at room temperature. They don't mind going cold. They're also happy to go hundreds of degrees C above room temperature. But because you don't need to bring along your vacuum chamber and your cryogenics, they're really something that's caught a lot of people's attention for making into sensors out in the world. In particular, this is an image, if you can see it, of different diamond chips with different colors, where each of those colors correspond to what the dominant defect is. And so one takeaway is that there are many defects. Probably folks are familiar with like canary diamonds, yellow diamonds. That's substitutional nitrogen. I don't think it's particularly useful for sensing, but the red arrow or the white arrow is pointing out that one of these chips glows red, and that's because it has a lot of these nitrogen vacancy centers in Diamond, which, as the name suggests, one of the carbon atoms is replaced with a nitrogen. Its neighbor is just vacant, the carbon atom's missing, and you get something that's the spin 1 electronic spin. It has either a spin 1/2 or spin 1 nuclear spin, and you have basically this qubit that's trapped in your lattice, ready to go for whether it's computing, networking, or in particular what we focus on, sensing. It's Hamiltonian, gives its sensitivity to magnetic fields, electric fields, temperature, pressure, strain. And what's fantastic is that actually the way the different ground state energy levels in this pseudo-atom move around, you can tell the difference between those things. So you can have a multimodal sensor and not get confused between temperature changes and magnetic changes. Well, the interesting part of the slide's covered. You can take a single one of these defects and do a lot of amazing things, really high spatial resolution. Imagine putting one of these at the end of an AFM tip and creating really, magnetic images with that kind of tens of nanometer spatial resolution. There's folks and companies doing that. Nanodiamonds, you can functionalize their surface. You can put them inside of living cells and use them as local temperature probes. There's a lot of fantastic both academic work in this area. And then kind of the area that we're most focused on is ensemble measurements, or devices where you're averaging over many of these defects in order to essentially, square root n advantage and improve your sensitivity and speed and how fast these measurements happen. Again, the sun is killing us. So if you take away one thing about NVs, it should be that on the y-axis here, we have magnetic sensitivity. And on the x-axis is resolution. And there's kind of millimeter scale magnetometers, vapor magnetometers, squid magnetometers, folks are familiar. Yes. That's already a little bit better. So basically, as it moves around here, hey, all right. Thank you, that helps a lot. So basically, the key thing is that diamond occupies a pretty unique space in terms of combination of spatial resolution and magnetic sensitivity. Of course, there's many other axes that matter, dynamic range, biocompatibility, but just to give you a sense, there's a space where diamond kind of is kind of the only game in town. And the result of this is that combined with some of its other properties, there's a wide range of different directions that people are going and that we're interested in developing. And this is, again, a piece of this quantum catalyzer model is there's a lot of commonality if you're building a magnetic imaging tool to look at currents in electronics, which I'll talk more about. It isn't actually, there's details that are very different, but a lot of the physics is very similar to what you need in order to have a bulk magnetometer for magnetic navigation in GPS-denied environments, for example. And then there's all kinds of interesting things of, diamond is very robust. Can you put it in harsh environments like nearby to fusion reactors? A magnetometer that survives is the best magnetometer in that situation. And it's certainly a terrible environment for any material. So one modality in particular that we've kind of pushed on first is this wide field magnetic imaging. Just imagine, as a tabletop microscope, and this is something that we're building and selling today. This is an example of, a quantum technology, a quantum sensor that is, real value and is available now and doing things for folks. In the real kind of special sauce for this is that you can, because we're doing optical measurements of the magnetic field, you can combine the bright field image and the magnetic image, co-register these with the same optics. And so co-registration is trivial. So this is actually George Washington's eye on the dollar bill. And there's magnetic ink for counterfeiting or for some reason. And we can kind of compare those two things. And that's what we're toggling between. And of course, sometimes it's nice to look at a millimeter square field of view, but then dollar bills are actually much larger. And so you can tile, you can raster scan and cover much larger areas. And so you have this wonderful dynamic range spatially from micron to millimeter. Just so that folks feel like they have something concrete and understand what's going on, we start bringing the diamond close to a sample. That sample can have magnetic sources, currents, magnetic materials that are going to perturb those ground state energy levels of the NB. Remember, it's like an atom. And then if we use the right combination of green light and microwave control, we're able to map the magnetic information, the magnetic field they're sensing, to the amount of red light, amount of red fluorescence we get. And then you take that fluorescence and you put it on a camera and you have a magnetic field map. And so that's kind of an example here of where the color is the intensity, the strength of the field. The intensity of the color is the strength of the field, and then the color is the polarity. In this case, whether it's pointing into or out of a decapsulated chip. So kind of pulling on that theme on the chip side, we go from we have this platform technology. It can be turned into this kind of microscope modality. What do you do with it? What's the kind of specific application? In this case, our portfolio company Euclid is pursuing applications in electronic systems, either from kind of a reliability angle, looking at current flow for failure analysis, inline inspection, design correlation of intact devices, so to tell you about functionality. But there's also kind of a dual use hardware security angle. Is your chip doing what it's supposed to? Is what's there what's supposed to be there? And that we kind of have an insight into this and a side channel that folks haven't thought about before because this tool did not exist. Again, though, it's kind of using this platform technology, packaged up and developed and applied to a very specific application. So, for example, the CEO of this company is a veteran of many years in the chip world at TI and Cadence. And so, kind of making this connection between the physicists and the people who, know the problems and building this bridge that's really critical to success. On the commercial side, there's some really interesting challenges coming with advanced packaging and 3D and heterogeneous integration, where magnetic fields will pass through most materials unperturbed, but that's certainly not true for IR or thermal photons. A metal layer will about kill them. But then also similarly, backside power delivery, power devices are nice because large currents mean large magnetic fields for us. And then, equally so in the battery space, both for quality control and not just knowing if a battery is bad, but having a sense of why it's bad because you have a little bit more information about what's going on, as opposed to what a charge-discharge cycle would give you. And this application is leveraging that kind of combination of sensitivity and spatial resolution, but it's also taking advantage of the fact that NVs are particularly good at measuring small changes in magnetic field on top of a large background. The case of many batteries is ferromagnetic, and it's a huge background field that you're looking for small variations due to a current. And then, this isn't the first time that people have thought about magnetic imaging for this electronic space. But with the advantage of being a room temperature system that's a lot more robust. There's no cryogenics, there's no vacuum, and I think that that coupled with this tunability is really kind of a unique combination to solve the problems that these communities and these folks are facing. Of course, not go. So just to kind of drive things home, we're looking at both chip scale imaging. You can go to board level, we look for delamination, other problems like this, and then also at the device level. And so you can span, this is 1,000, 10 or 3 orders of magnitude that we're kind of tuning over. And you can similarly, stay at the high level and then see something interesting and plop down and take your higher resolution image. And so this tunability is really, really a key aspect. But of course, the magnetic field maps are only half of the story, because usually failure analysis engineers and others want to look at currents and localize the currents and understand, is there something flowing, is it not there, how strong is it? And so this current reconstruction problem is a key piece of what we're up to within Euclid. Essentially, if just in one line, was this idea of teaching a neural network Biot-Savart's law, or teaching it a little bit of physics to solve this magnetic inverse problem, to go from magnetic fields to currents. And in particular, especially in 2D and 2.5D, there are analytical approaches and solutions to this, but they're quite vulnerable to noise, and if you have currents that are flowing outside of the field of view. And so the ML approaches provide an advantage there. And then in 3D, these inverse problems are not uniquely solvable. Many current distributions could create the same magnetic field map, and so the trick becomes figuring out how to correctly combine other prior knowledge, about the structure of the chip, or maybe you did X-ray imaging and understood the structure from that, and combining that structural information with your functional magnetic imaging information. And just to give a sense of how quickly, if you have standoff from some packaging, you have nice currents that are very well defined, they get very blurry very quickly, but that information is still there, and you can go back to localize those currents quite well. So just to kind of conclude things at the highest level, quantum sensors are something that, they can be a near-term concrete win for quantum technologies. And I think that we can be excited about, where the larger, not too distant markets are in electronics, but also in plenty of other directions, health, harsh environments, just within this kind of NV diamond world. And then I think one of the most exciting things is that, this is a very vibrant research community of solid state defects, other defects in diamond and in other materials. I think it's an exciting time, just that it turns out there's a lot more defects that behave quantum mechanically than I think we maybe would have suspected. But now we have the tools and technologies and are looking for it. And so I think that's the future here is pretty exciting. With that, thank you. Maybe I stay close to 15 minutes.